is that after the talk, whether it's 4:30 or not, ends, there will be buses waiting for us, okay? Now, okay, I guess there is no... Ma? Oh, Merale, here, we can start. לא חשוב, שב. מרלה. איבדת את הזהות שלך. אוקיי. אפשר לסגור את הדלת שם?
עוד באים על המדרגות עוד מלא.
לא להיכנס עם שתייה. טוב, אוקיי.
זה נכון, אבל...
Welcome to this last session of today. There's no need to introduce our next speaker. It's always a great pleasure to listen to lectures of Bob Aumann. And in particular, he has a nice series of lectures which he calls My X. No, that's not what you think. X
is a variable.
X is a variable. X is a variable. It stands for the first name of a previous PhD, not previous, but past PhD student of Bob Aumann. So for today's lecture, for instance, X equals Merale. Okay? So that's the point. I don't want to take more time of Bob, but just about the cardinality of this set, capital X, which is the domain of X. It's at most countable, but there's no proof that it's finite up to that. Okay.
Okay, so we'll start with a tasting menu. We'll start with a reminiscence, and then some apologies, and then hors d'oeuvre, theory versus action, and then we'll talk about the Shapley values of non-atomic games, to which Merale really is an atomic player. Yes, okay. An atom in that non-atomic continuum. And we'll talk about bounded rationality and stochastic games a little bit. We'll do we'll just do the tip of the iceberg that Merale presented in the previous talk, and that's it. So let's start with the reminiscence, which really has nothing to do with Merale, nothing at all. It's 50 years exactly since the first international workshop, the first international game theory workshop in Jerusalem in 1965. It's the 50th anniversary. So we've been doing international gatherings in Jerusalem on game theory for 50 years, yes. And we're still going strong, very strong. The participants at that workshop were right here. I think these are all the participants. Hassani, Isbel, Kuhn, Lucas, Marshall, Parthasarathi, Peleg, Rosenmüller, Scarf, Selton, Shapley, Shubik, Stearns, Thrall, and your humble servant. And those in red, what?
You used to say 17, so you're missing 2.
No, אני חושב שזה 15. I think so. I'm not sure, but so, you know, I had the word some participants in before, but where's TN? Is he in the room? Hello? Not in the room. Hi. Okay, so the three of us, Peleg and you and I, are the only survivors of that. I mean, in Jerusalem. What's that? No. Schmeidler didn't exist yet. Nobody here existed. Merale didn't exist. He wasn't born. He was a teenager. Yes. So that's it. And we've come a long way. And let me tell you in which way we've come a long way. That was a workshop that took 3 weeks, not 3 days, okay? It took 3 weeks, and there was one lecture a day. One, yes? And it lasted about an hour, maybe 2 hours, something like that. So now we have 3 days instead of 3 weeks, and we have, what is it, 100 lectures a day lasting? Something like that. So we've really made progress. Okay, and now some apologies. First of all, to the speakers, and I'd like to apologize to almost all the speakers that I haven't been coming to the talks. And the reason is twofold. First of all, I had to prepare this talk. Yes, that's number one. Number two, and more important, I now admit to not understanding mathematics. Okay, I don't understand. I never understood mathematics at talks. I used the time in talks to think about my own problems. Yes, but now I admit openly to not understanding mathematics, and I think it's okay because I gave up skiing last year, so I can give up mathematics a fortiori. Yes. Okay. So that's to the speakers. The second is to Merale, because I will really only touch on very few of his results. And I mean, his work, I think, is really amazing, both in breadth and especially in depth. Yes, I mean, he's really, his work is totally, I'm really carried away with it. And I'm going to talk about very, very little of it, and not the most important stuff maybe, and certainly not the most recent stuff. On the contrary, it's some of the oldest, yes. So my apologies to him. And last, apologies to Nash, because at the Nash session tomorrow afternoon, I will not be present. I have a previous engagement which I entered into several months ago. I can't make it. I can't tear myself apart. And but I have tremendous respect and admiration for John Nash, because he was the guy who taught me game theory in the first place. I first heard about game theory from John Nash, and what led me into game theory was those conversations with him, although in a roundabout way, which I won't go into now. Okay, now let's talk about the first real item on the tasting menu, and that's theory versus action. This is the over here we are sitting in the Federman Center for the study of rationality. We're not sitting in the Federman Center for rationality, okay? So people sometimes I try to explain to them what rationality is in this building, okay? What it means. It's not what rationality usually means everywhere else in the world, but it's economic rationality. It's acting to advance your interests in the light of the information that you have. So they say, oh, so you are rational? I say, no, we're not rational. We study rationalities. Yes, entomologists are not bees, okay? We study rationality. We are not necessarily rational ourselves. And that leads us to game theory, which is the name of this conference, right? It's a conference in honor of Merale and Neyman, but it's called game theory, and there's a big difference between game theory and playing a game, and in particular, the game of chess. Okay, and let me tell you a little story. Okay, about Merale. Merale had started doing a doctorate with me, and I saw he was a bright kid, and so I gave him a difficult problem to solve for his doctorate, one that I couldn't solve and that Lloyd Shapley and I couldn't solve. With combined efforts, we couldn't solve it. So I gave this problem that we tried. It's not that we didn't try. It's not one of those things that, we tried very hard to solve the problem and we could not solve it, okay? So I gave it to Neyman to do for a doctorate. And a few months passed, and half a year passed, and a year passed, and he wasn't making any progress with it. Now, I knew that he is I don't know whether professional, but certainly a top-class chess player. And he engages in tournaments, and I said to him one day, I said, what's happening to you? So he said, tomorrow I have to play in this tournament, or next week, or so on and so forth. Yeah. So I said to him, Abraham, you're going to have to decide. You want to play chess? God bless you. You want to do mathematics? God bless you. But make up your mind. If you want to do mathematics, you have to give up chess. You can play chess, occasionally, but this intensive playing tournaments, this is not going to go. So he said to me, give me a week. I'm going to think it over, okay? Give me a week, yes, before I go to the guillotine. I said, fine, very good. You have a week. So after the week is over, he comes back and he says, I choose mathematical game theory. And the rest is history, okay? He solved the problem, by the way, within a few months, I think 3 or 4 months or something like that, after giving up chess, okay? All right, so that is that story. So now we will go to the next item on our tasting menu, and that is Shapley values in non-atomic games. So first of all, people ask me whether this is open to the general public, so to speak. So I said, well, maybe yes, partly. So we're going to try to keep it simple. The Shapley value of a player in a game is a measure of his usefulness or productiveness, his contribution to society, in other words, to the game as a whole. Okay, a game is a very complex object, and you take a very complex object and you try to sum it up in basically for each player in one number. It's going to be you're going to lose a lot of information there. It's like when you take a distribution and you take look just at the mean of the distribution, okay? Just take a lot of numbers, yes, your all your grades in the university, and you take just the average, all right? You lose a lot of information, but it gives you some idea. So that's what the Shapley value of a player is. Now, what's a non-atomic game? Merale was talking about continuous time. Here we have a continuum of players, okay? We have lots of players which we model by a continuum, and the contribution of each individual player is infinitesimal when you compare it to the society as a whole. So examples are large economies. You look at the economy, say, of Israel, not as consisting of 8 million players, but as a continuum. Or you could look at it as a polity, voting games in Israel or in the whole world for that matter. Yes? And in fact, one of the subjects that Neyman studied was the economic political games, and we'll have more to say about that. And games with finitely many players, the value is uniquely determined by a few reasonable conditions. You put some conditions, and that determines the value. Now, to define values in non-atomic games, games with a continuum of players, one takes the game and one approximates it by a large finite game. It approximates it by a large finite game. And then you let, in other words, games with more and more players, and then you let the number of players grow to infinity. And you look at the value in each one of these finite approximants, and then you see what happens to that value when you go to infinity. Now, I won't go into the details here. If somebody wants to the details are quite complex, but this is the idea. You approximate by a large finite game, and then you let the number of players go to infinity. Another way of approaching it is to give reasonable axioms on the non-atomic game as such. And these two may fail to define the value uniquely. Which by that we mean is they may fail to define the value altogether. There may not be anything that satisfies those axioms. Or it might be that you don't get a unique payoff. In other words, a unique result. You could have you could have several values that satisfy the axioms. But and as we said, the asymptotic game, if it exists, the asymptotic value, if it exists, it exists. But it may not exist. But in any case, if it exists, it's unique. So, and when it exists, the asymptotic value, what you get by finite approximants, it does satisfy the axiom. Now, we call a value diagonal if it depends on a player's contributions to coalitions that are almost representative. Only coalitions that are almost representative. What we mean by representative is that if, for example, you have a coalition of Arabs and Jews in Israel, then that coalition would have to consist of approximately 78% Jews and 22% Arabs. It could be small coalition, large coalition, but almost represent. And that in all respects, in all measures, whatever you look, however you look at the coalition. So this is a very, very special kind of coalition. But we found in the preliminary studies, before Neyman came along, and in preliminary studies of values of non-atomic games that Lloyd Shapley and I undertook, we found that all the values we came across, the asymptotic value when it exists, or the axiomatic values, all those that we came across had this property that they were talking only about coalitions that are almost representative. Okay? And now we call a value continuous if it assigns similar values to similar games. It's the usual notion of continuity. You change the game a little bit, it doesn't change the value a lot. Now, I asked whether we could keep this slide on the someplace on the screen or on one of these two screens while I put on the next slide, but I was told that that is impossible. Yes, we have progressed. Yes. It used to be possible under older technologies. Yes. Nowadays we have progressed to a point where that is impossible. So you will have to keep those things in mind. All right, keep all these definitions in mind, and we will examine you on them later. All right. So now we talk about the contributions of Merale to value theory. Okay, and I emphasize the word theory because we'll get to an application by and by. Voting and many other discontinuous games have asymptotic values. Now that is the little problem that robbed Merale of his chess career. Yes. A voting game, you see, is discontinuous. When you look at it when you look at the player set as a continuum, then there is a point where you pass the 50% mark, okay? And up to 50%, you lose. A little beyond 50%, a little bit, you win. This is a discontinuous game. The game itself is discontinuous, okay? When you look at the game as a function of the coalitions. And this is where Shapley and I we did not manage to solve this problem, the asymptotic values of voting games. And in fact, Neyman, in really a remarkable tour de force of combinatorial reasoning, he managed to prove this. The thesis was done in 1977. It was published in MOR in 1981. Now, I said before that the values that Shapley and I found were all diagonal values. In other words, they are all values in which what matters is only almost representative coalitions. And Neyman, together with Aumann, found a value, something which satisfies the axioms, which is not diagonal. This was published in MOR in 1976. And then Neyman proved that continuous values, which means values which depend continuously on the game, are indeed diagonal. And he did many more results in value theory throughout the years. And these are his these are some of his contributions to value theory. Now I'm going to talk about an application of values. Okay, in two related papers, and these were in the Review of Economic Studies in 1983 and Journal of Economic Theory in 1987, Neyman and Kurtz and your humble servant investigated the value of a non-atomic economy which has two kinds of agents. We have the taxpayers, okay, and all agents are taxpayers. All agents in the economy are liable to taxes. But there are also citizens, okay, and only citizens can vote. And when you vote, you determine what public goods are going to be produced, okay, and how they're going to be paid for, okay. So the tax regime, the tax laws are passed by, let's say, some kind of parliament or something like that. And this parliament is elected only by citizens, okay? The non-citizens have nothing to do with it, okay? Now, in that kind of situation, these are, by the way, non-exclusive public goods, okay? So we're talking about public goods that anybody can use. Roads, parks, television viewing, if you wish, non-commercial television viewing. This is public libraries, whatever. Okay? Now, in this kind of situation, the voters' taste and budget is obviously that what's going to be produced is the kind of public goods that the citizens like, right? The voters, and they're going to try to impose taxes on the non-citizens, perhaps in some way. So what's going to happen is, since it is only the citizens that vote, what's going to happen is that they're going to get what they want, right? There's a rule in lectures that Aumann gives. When he says right, then the answer is no, wrong. Okay? So in fact, the vote counts for nothing. Nothing. The resources and tastes of all agents, citizens or not, determine the outcome. So in other words, people, all the agents, all the taxpayers, whether they're citizens or not, they have some resources, they have some money, they have whatever it takes to produce public goods. And they have preferences, they have tastes, and that's what determines the outcome, that determines what is predicted by value theory in this game. So that sounds crazy, okay? It sounds completely crazy, totally counterintuitive. But this is not the first practical application that was analyzed by means of value theory. And it happened previously also that value theory gave surprising results. And then when you looked at it carefully, it makes sense after all. And the same thing happened over here. Very briefly, the reason is that in a cooperative setup, votes can be bought, okay? I can buy your vote, yes, and the people with the resources, even if they're not citizens, can buy the votes of the citizens, okay? Money speaks, right? Now this, and then the fact that only 51% of the vote is needed, all right, to pass any resolution, and competition. So the voters, the citizens, are basically competing with each other to sell their votes. And there's a reason that their vote is worth much less than their preferences on the public goods. Don't have time to go into this now, but a thorough analysis shows that it's true that the citizens have preferences on the public goods, but the money that they can get for the vote, in theory, is worth much more than their preferences for public goods, and this drives the price of a vote to zero. Now, notice that what's happening, if in order to sell a vote, you have to be able to deliver, right? So the vote has to be non-secret. In this model, the vote is not secret. So this highlights a fundamental reason for secret voting. It's not to protect voters. It is to protect voters, but not from pressure or threats, but from themselves. That otherwise they would want to sell their votes, yes, to their own disadvantage. So this is a situation in which value theory at first leads to a surprising result, but then the result turns out to be interesting and to give an important insight. Now, we go to the next item on our tasting menu, and that is bounded rationality, and specifically automata. In the only equilibrium of the 100 times repeated prisoner's dilemma, PD of 100, both players play greedy at each stage. Okay, I think most of the people in this room know what a prisoner's dilemma is, and those who don't, I'm sorry. It's like the time that the plane had to make an emergency landing in the ocean, and they said, please, will all those people who know how to swim go to the right side of the plane, and all those who don't go to the left side of the plane. It's only to keep the plane in balance as we are doing this emergency landing. And then the plane does the emergency landing on the water, and the pilot comes on and says, ladies and gentlemen, there's some problem with the inflating the rafts. Yes, we have a problem with that. So there's an island 300 meters to the right. The people on the right can swim to the island. The people on the left, thank you for flying El Al. Okay. Okay. So this is all right. We won't say any more. So in the 100 times repeated prisoner's dilemma, as it's known, the only equilibrium gives the bad result. And this leads to some discomfort. One feels that some cooperation should be possible in the 100 times repeated prisoner's dilemma. Now, this game, 100 times, the prisoner's dilemma itself has only 2 strategies for each player. But when you repeat it 100 times, it's not 200 strategies for each player. It's 2 to the 2 to the 100. Something like that, yeah. In enormously many pure strategies. And the idea that all are available to the players is totally absurd. Now, Neyman, in really a breakthrough paper, a seminal idea in Economic Letters 1985, proposed restricting strategies to those that are programmable on an automaton. And an automaton is a computer, okay? He then showed that even when the computer is very large, not arbitrarily large, but very, very large, an outcome that is almost exclusively friendly, a good outcome, may occur in equilibrium. Okay, when you don't allow any old strategy, but only those programmable on a very large computer, then an outcome that is the friendly outcome survives and is possible in equilibrium. And this goes very far to dispelling the above-mentioned discomfort, because it's a very intuitive idea that you can't use all strategies, only strategies that are programmable on a computer. More generally, Neyman proved the folk theorem for the n-fold repetition of an arbitrary game G when the size of the computer is sub-exponential in n. Okay, here again I may lose some of the audience, but I hope some of you to understand this, and he wrote many other papers. For example, when computers' sizes are unequal. The next item that I wanted to mention was Stochastic Games, on which we heard Merale's lovely lecture just previous to mine. And let me say some of the things he said in slightly different language. So a stochastic game is like a repeated game, so it's an ongoing situation, except that you don't repeat the same game again and again. It may change, the game may change from period to period, depending on what the players have done before. So the current actions determine the current payoffs and the future opportunities. So as we heard from Merale, Shapley was the first to formulate this idea. He formulated stochastic two-person zero-sum games and showed zero-sum. So he showed that the value exists for fixed discount rates, discounted what Merale called impatient, okay? One kind of impatience, yes, one kind of impatience. For a fixed discount rate, the value exists, and he indicated how to calculate it. Bewley and Kohlberg showed that the limit of this discounted value exists, and also it's the same as the value when you cut or truncate the game. Don't discount, but truncate the game after n. That's another kind of impatience. Truncate the game after n periods, and the limit of that as the impatience gets smaller and smaller, they exist and are equal, but they did not succeed in showing that in the patient game, which is the infinite stage game with no discounting, that the value exists. And this was done by Mertens and Neyman, which was a really, the theory has progressed since then, but this is really the cornerstone of the theory. At that point, it was a very important paper, and it was, I think, generated at the emphasis year in game theory, which took place in 80-81. Is that correct? Yeah.
79-80.
What? 79-80. It was generated there. Yeah. Okay. Well, Mertens was there, and Shapley, and many others. Dubé had just gotten married and did his honeymoon in Jerusalem here. Okay. So the significance of these things, I think Neyman explained the significance of these things, and the buses are waiting. So let me just say this, though. The optimal strategies in the infinite stage game are approximately optimal in each sufficiently long finite stage game. So in other words, the infinite stage game is a way of saying, here, if a player knows that the game is long, but he doesn't know how long he should play to get the value v infinity. That's a big difference between looking at the game, the infinite stage game, as a limit of impatient games. Because in impatient games, the strategy is different for each. If you truncate after n periods or after 2n periods, the strategy is different. If you solve a game with a discount rate delta or a half delta, the strategies are different. In the infinite stage game, these are not optimal in the finite approximants, but they are approximately optimal. So this is a way of looking at at long games, but you don't know how long. So you just play to get for V infinity. I think we will just say happy birthday, Merale, over here. And Toda, I always say this in the language of the country where I'm giving a lecture. And if I would be giving this lecture in China, where I have often given a lecture, you would see the Chinese characters for she she, but then I say it in English also. Questions?
I guess any remark or question? Otherwise, in the past, we can continue.
Okay.